We'll continue the relativistic quantum mechanics series, and this is the second video in this. And here will be studying about Klein quantum equation, okay, which is a very important equation. So relativistic quantum mechanics will continue. Okay, so Klein quantum equation. Klein quantum equation. Okay. So from elementary quantum mechanics, what we have studied. From elementary quantum mechanics, we know the Schrodinger equation. Okay, if I write the Schrodinger equation, by I h cut del psi by del t is equal to minus h cut square 2m naught del square plus vx, okay, psi x. Is that right? Yeah. So where E is what, like suppose non-relativistic energy operator, non-relativistic energy operator. Let's see. That will be what E, okay, E cap. That will be P square by 2m naught, yeah, plus Vx. Again, where what is P? Okay, if I also write it as E is equal to I h cut del by del 2, and P is equal to minus I h cut del 2. Okay, yeah, we know this. So this is a momentum operator. This is your energy operator. Okay. Okay. In order to obtain relativistic wave equation, what will you do? Okay. I will consider free particles with the relativistic relation. I will write like this, like momentum 4 vector. We have studied this. P mu. So E square by C square minus P dot P. We have studied this, right? Yeah. So we can write it as M naught square C square. Okay. So we can replace the 4 momentum P mu by the 4 momentum operator now. If I can replace P mu is equal to I h cut del by del x mu. Okay, this is contrast. This will be covariant. So this will become I h cut del by del ct minus del by del x minus del by del y, and this will be minus del by del z. Okay, so this will become I h cut del by del ct minus del. Okay, yeah. So this is your zero component always, and this is your simply gradient. So I can, like if I multiply h cut inside, so I h cut del by del ct minus I h cut. So I can write this as, this one will be the zero component, the fourth momentum vector. That will be p zero cap. This is your p. Okay. Yeah. So if we like, okay, let me do one thing. Let me give it an equation. Question one. Okay. So suppose like right now P mu psi is equal to m naught square c square psi. Okay, can you write like that? Okay. So m naught is what exactly? M naught is the rest mass of the particle, c is the velocity. So now what can I do? See, we can use some equations now. Okay. Let me write one thing. You have to tell me whether it's correct or not. If I use D'Alembert's like operator here, plus m square c square divided by h cut square is equal to what? Is equal to del square c square del t square. Okay, minus del square del by del x square minus del square by del y square minus del square by del z square, right? Plus, okay, sorry, plus this is your D'Alembert sorry, operator. This one is still there, so I will write that also. Plus m naught square c square divided by h squared square. Okay, yeah, and we can write psi is equal to 0 because this is equal to exactly 0. Okay, so we can immediately verify Lorentz covariance of the Wayne-Gordon equation. Okay, and from that we will realize that p mu is actually Lorentz invariant. Okay, Lorentz invariant. Yeah. So if I try to solve this equation, what will I get if I try to solve psi? So psi I will get is exponential, like we used to get in quantum mechanics, minus I by h cut, okay, p mu x mu, right? P mu x mu. So this will become exponential minus I by h cut. P mu x mu I can write p0 x0 minus p1 x1 minus p2 x2, those things. So I can simply write this p vector dot x vector, right? Yeah, right. So I can take the minus inside, or do one here. Um, yeah, let's take the minus inside exponential. Um, let's take the minus inside I by h cut p dot x minus p naught x naught. Okay, p dot x minus p naught x naught. Okay, p naught x naught is anything there. P naught x naught. Can I write something? This is p naught x naught. P naught x naught. Okay, p naught is what? P naught is x naught is what? X naught is ct. P naught is what? Del by del c, isn't it? Right? So if you see exactly this one, and, I sorry, yeah, uh, P naught is, yeah, ct or something like that. Okay, so if I do this term, I will get exactly like et or something. Okay, so I will put in place of it et. So exponential I by h cut. Just check it, okay? P dot x minus et. So now what will I do? Now I will put this psi in place of this one, okay, or in place of this one. I will put psi, the value of psi, and I got here. So if I put the value of psi, so p mu psi is equal to m naught square c square psi. Okay, so that gives me p mu exponential, okay, exponential minus I h cut minus I by h cut p mu x mu, okay, is equal to m naught, the right side m naught square c square psi is exponential minus I by h cut p mu x mu, right? Yeah, so this is I'm getting on the both sides. Okay, so this will give me something like what, e square minus by c square minus p dot p will be equal to m naught square c square. So this will give me this. This will give me this. Okay. So this is your what? So this will automatically give me, if I see e square by c square is equal to p square plus m naught square c square. So e square is what? E square is P square C square plus M naught square C4. And if I take the root over, it will be E is equal to plus or minus root over of P square C square plus M naught square C square. So if you see, we are getting two values of E, that is our plus or minus. We are getting, so both positive and negative value of energy exist here. Okay. So from at a later point, we will see that this negative energy, suppose, is a minus m square c square plus m square c4. This negative energy is actually associated with antiparticles. Okay, these are associated with antiparticles. Okay, since antiparticles can indeed be observed in nature, we have already obtained an indication of the value by extending the non-relativistic theory. Okay. Yeah. So energy spectrum, if I draw an energy spectrum of plane Gaussian equation, so this is a E, so this is something like this. This is a positive m naught c square, and the lower part will be a simply negative m naught c square. So you can write it as something energy spectrum of the free plane Gaussian equation, that is KG equation. Okay. Yeah. Yeah. So this is a bit mathematical, and you have to kind of do it again and again to understand. Okay. Next is what? Next we will derive um, uh, 4 current, that is called J, derivation of 4 current. 4, it's called 4 current. Actually current density. Okay, it's called 4 current J mu. Okay. We can do it J mu. So again, if I write the equation P mu minus m naught squared c square psi is equal to 0. Okay. So if I take the complex conjugate of this equation, so taking the complex conjugate, if I take the complex conjugate, it will be P mu minus m naught square c square psi star is equal to 0. Okay. Yeah. So this is a proportion of the equation 2. So multiplying both the equations from the left, the first by psi star and this one by psi. Okay. So what will I do? Let's multiply here only. Okay. Psi star here, psi star P mu minus m naught square c square psi is equal to 0. So let's give this equation as 1, and psi here, so psi p mu minus m naught square c square psi star, that is equal to 0. This is equation 2. Now what will I do? I will just subtract them. Okay, I will just subtract these two equations. Subtracting 1 and 2, what will I get? Psi star p mu minus m naught square c square psi minus psi p mu minus m naught square c square psi star is equal to 0. Okay, equal to 0. So what will I do now? What will I do now? See, p mu can be written as what? Minus I h cut del mu, right? Del mu. Del mu. So let's write it. So psi star minus I h cut, okay, del mu, and again this one also minus I h cut del mu minus m naught square c square psi minus psi. Okay, minus I h cut del mu minus I h cut del mu minus m naught square c square psi is equal to 0. Okay. Okay, so this you are multiplied minus 1 minus, so h squared square, I'm getting h squared square. Okay. minus. So psi square minus h cut square del mu minus m naught square c square psi minus psi minus h cut square del mu minus m naught square c square psi is equal to 0. Okay. Yeah. So what will I do now? I'll just simply multiply them and take them inside. So see how I'm taking them inside. Minus h cut square. Let's take it out. Okay. So it will be like psi star. Um, let's do one thing. Um, okay, let's completely expand this. Okay. Minus h cut square psi star del mu psi minus psi star m naught square c square psi plus h cut square psi del mu psi plus psi m naught square c square psi star. See, if you can see, these two will be cancelled out. Okay, minus plus. So these two are only remaining. So if I write them, so minus h cut square common. Okay, I will take del mu as common. Okay, take del mu as common. So it will be like psi star del mu psi minus psi del mu psi star. Okay, yeah, like this is my bad. Yeah, is equal to 0. So if you see h cut square goes to the other side, so del mu of psi star del mu psi minus psi del mu psi star is equal to 0. Okay, so this is actually your current density vector for vector, that is j mu, because this is mu here, mu is control variance, j mu is equal to 0. Okay, so therefore we can write this as j mu. J mu is equal to psi star del contra j mu psi minus psi del mu psi star. Okay, yeah, and sorry, my bad, there is not a multiplication. I h cut by 2n now. Okay, yeah, because we have multiplied this just to have the dimension of probability current density. Okay, all right. So if you remember, okay, this is your equation. Correct. If you remember the continuity equation, if you remember continuity equation, which is what? What is the continuity equation? Hmm. So if I write the continuity equation, del by del t, I h cut 2 m naught c square psi star del psi by del t minus psi del psi star by del t, okay, plus divergence or divergence minus I h cut by 2 m naught, okay, psi star del psi minus psi del psi star is equal to 0. Okay. So from here we can write what? Del phi by del t plus del dot j is 0, we know it, right? Yeah, we just put that. Okay. So this is your kind of current density amount. Okay. Yeah, just go through it once and then only we'll move forward. Okay. Do it once yourself also. So you can, okay. Okay, let's move to the next part. This is the non-relativistic limit of Klein-Gordon equation. Okay, so we're reading non-relativistic limit. The non-relativistic limit. Okay, so we can study the non-relativistic limit of Klein-Gordon equation, and in order to do that, we can we have to make a assumption. Assumption that is psi rt, okay, is equal to psi rt is equal to phi rt, okay, phi rt exponential minus I by h cut m naught c square t, okay. Yeah. So if we split the time dependence of psi into two terms, one containing the rest mass, like um, so in non-relativistic limit, the difference of total energy E of the particle and rest mass m naught c square is very small. Okay, like this E minus this m naught c square is very small. Okay, m naught c square is very small. Okay, so we can define that as E dash is equal to E minus m naught c square, right? And this kinetic energy E dash is actually non-relativistic. It's not relativistic. We can say it's non-relativistic, okay? Which means that E dash is very small than m naught c square, right? Yeah. So hence we can like write something like IH cut del phi by del t, okay, almost equal to A dash phi very less than m naught c square phi. Okay, yeah. So we have what do we get from here? Let's write del psi by del t is equal to del phi by del t minus I m naught c square by h cut square. Sorry, h cut only m naught square h cut psi exponential. I'll just expand it. Okay, I'm just expanding it and putting the values here. It will be kind of approximately equal to minus I m naught c square h cut, okay, phi exponential minus I by h cut. You have to do it on your own. Okay, don't just copy paste. Only if you do it, only then you will understand it. Okay. If I take the double derivative of it, so I will get what? I will get psi del square psi by del t square. Okay. So let's take the double derivative del square psi by del t square. So I have to take the whole double derivative of this one. Okay. Yeah. Or this one first. Um, okay, let's take it in del by del t of del phi by del t minus I am not c square by h cut psi exponential minus I by h cut m not c square t. Okay, so I have to take the this one del square phi by del t square minus I m not c square by h cut del psi by del t and exponential this one. Okay, so I have to open it completely. Okay, you have to open it, and at the end you will get something like IH cut at the end. IH cut del phi by del t is equal to minus h cut square by 2 m naught. Okay, del square by del x square, del square by del y square, del square by del z square. Okay, phi is equal to minus h cut square by 2 m naught del phi. Right? Yeah. So this is the free Schrodinger equation for spinless particles. Okay. You can write this is free Schrodinger equation for spinless particle. As the type of particle which is described by wave equation, it doesn't depend on whether the particle is relativistic or non-relativistic. So we can say Klein-Gordon equation, Kg equation describes spin zero particles. We can write Kg equation actually describes spin zero particles. Spin zero. Right. Later on, we will obtain this important result in a totally different manner by making use of the transformation properties of Klein-Gordon field. Okay. Klein-Gordon field. There is another thing. All right. So this was all about your Kg equation. We will do more in the next section. Okay? Because this chapter we will have to move very slowly. Otherwise, you won't be able to understand a lot of things and it will be skipped. So yeah, that'll be it for today. Thank you very much.